advanced higher. This is Statistics Lesson 4, and in this lesson I'm going to deal with hypothesis building and begin the process of dealing with inferential statistics. Our learning intentions could be phrased as what do inferential statistics do and how do I build a hypothesis? And so, before we get started, I'm just going to deal with the first learning intention right now. In the previous lesson, lesson 3, we dealt with descriptive statistics, namely the mean, the mode, the median, standard deviation, interquartile ranges. And those statistical methods are good for drawing comparisons. You would be able to see detailed comparisons between two bars on a graph or between two columns of data in a table. With inferential statistics, what we're seeking to do is to see if two columns of data or two bars on a graph or two axes on a graph have an influence upon each other, whether one affects the other. So we're not just simply drawing a simple observed comparison, we're now seeing if two different data sets influence and impact upon each other, whether they have a relationship with each other. So let's get started. To start looking at inferential statistics, it's really useful to also get this little part of the course cleared up, and that's hypothesis building. I could have dealt with this at any point up until now, but I felt it made sense to just plug it in here. A hypothesis is basically a research question, and the first thing you need to know is that when we write research questions, we write a null hypothesis and an alternative hypothesis. The null hypothesis, as you can see in the yellow box, is basically the opposite of what the researcher is trying to prove. That might sound illogical to you. Why would I write down the opposite of what I'm trying to prove? The reason we write down a null hypothesis is because it removes bias from your methodology. And it's very important that you are always demonstrating that you have not biased your own results. So our research question is always phrased as the opposite of what we expect to happen. You'll see that I use the terms AH and NH for alternative hypothesis and null hypothesis. Let's look at some examples. An alternative hypothesis could be that there is a relationship between the speed of water in a river and the width of the river. I think that as it gets faster, it's going to get wider. However, I must phrase this as a null hypothesis. So the null hypothesis version of that would be there is no relationship between water speed and river speed. And I will allow the data to disprove that null hypothesis. Some people get tied up in this and they think that if the data does not agree with their alternative hypothesis, that they've somehow got it wrong. And you must get your head around that as quickly as possible. It doesn't matter if you prove the alternative hypothesis or the null hypothesis correct. What you are doing is you are showing that you have thought about, let me just get my laser pointer, that you have thought about your alternative hypothesis and you have considered the opposite kind of viewpoint of that hypothesis, and that you are allowing the data in an unbiased way to prove or disprove one of these two viewpoints. Here's another example with pebble angularity. And the reason I've put that second example in is just so you can see the different kind of phrasing that we might use. For our example, in this lesson, I'm going with something that you'll be familiar with, so let's talk about exams. And I'm saying there is no difference, because it's a null hypothesis, I'm saying that there will be no relationship. There is no difference between the average number of hires passed in two different schools. And my alternative hypothesis, therefore, is that there is a difference between the average numbers of hires passed in two different schools. And I will allow the data to prove or disprove which of those statements we can accept as true. Obviously, we're going to apply some statistical tests to the data, and whichever of the hypotheses, the null or the alternative hypotheses, is proved correct, that's the one that you accept. It doesn't matter which one is accepted, that's the one that you will accept, and that is how you will conclude your analysis of that hypothesis. Okay, on to the second part of this lesson, which is inferential statistics. Inferential statistics, as I mentioned earlier, are not about making comparisons. Those are the descriptive statistical tests we talked about in lesson 3. Instead, inferential statistics make inferences, and if you look up the word infer, it's all to do with deducing something, making a conclusion. And what the conclusions we are seeking to make are that there would be relationships between data sets, that one data set is having a causal relationship upon another. In previous lessons I've referred to the number of donuts that I eat having a causal relationship with my weight. Now, one data set may have an influence on the other, and using statistical tests, inferential statistical tests, we would be able to establish if there is indeed an influence between the donuts that I eat and my weight. We are interested in finding out if there's any difference between the average number of hires passed between our school and another school. This will be there's very likely to be a difference, but the question we're looking to answer here is when does that difference become significant? When does it become a meaningful one? And to answer that kind of question, to answer if there is a relationship between two sets of data, if one is influencing the other to a significant degree, we use inferential statistics. Basically, if you look at bullet point 4, over the next few lessons, I'm going to show you a series of calculations that you can do. Each calculation is more appropriate in some circumstances than others, and each calculation gives you, at the end of it, a score. And you use that score, and you compare it to a statistical table. And when you look the score up on that statistical table, you will know if you can accept your null or your alternative hypothesis. There are a number of different inferential tests that I will teach you. Spearman's, commonly known as Spearman's, it's actually Spearman's rank correlation coefficient, to give it its full name. Pearson's, or Pearson's product moment correlation coefficient, to give it its full name. Chi-squared, and linear regression. There are many other statistical tests, like the student t-test, Mann-Whitney test, which you will find in your textbook, and that are really powerful, effective ways to test certain hypotheses, and you are welcome to make use of them. None of them really are any more difficult than each other, in my personal opinion. So, when we carry out these mathematical tests, we're looking to find out how significant our data is. Significance is a really important word to talk about here, because when I say that the relationship between the speed of the water and the roundness of the pebbles is significant, because the statistical test I have done has given me a score that when I look it up on my statistical table, it tells me that yes, it's significant. what that's really saying is that there is a very low probability of chance. In other words, when you get a score from doing your statistical tests that meets or beats the value in your statistical table that you've been given, or that you can download, by the way, on the same page as you'll find these videos, then there must be a very low probability that pure chance is causing the relationship that you are seeing. And that is essentially, at all stages in this lesson and the next lessons, what we are seeking to prove. We're eliminating the probability of chance by using mathematics. We're saying that, is there a relationship between water speed and pebble roundness? Well, I don't know, so I will apply a statistical test. I will apply an inferential statistical test because I'm trying to establish if one thing is having an impact on another. And that statistical test will eliminate the probability of any relationship that I do see being the result of pure chance. Now, the significance levels that we use are 0.05 and 0.01. What does that mean? Well, they are the chances, our certainty out of 100 that the event did not occur by chance. So if you have a score of 0. If you are able to beat the score in the statistical table that I've given you at 0.05, what that means is that you are 95% certain that the result you have seen in your graphs and your tables is not the product of chance, and that there is a relationship. And if you are beating the score in the statistical table at 0.01, then you are 99% certain that chance is not the factor that is causing the relationship, but that the two things you've measured, river speed and pebble roundness, for example, that they are influencing each other. Read through the information on this page a couple of times, because it just gives you a little bit more insight into where we get these values of 0.05 and 0.01 from. The statistical table I'm referring to is called a critical values table. And as I said, you've been given that in class. You should have that stuck in your jotter. But you can also download a copy from the website right here if you've lost it, or you prefer to have a digital copy to work with. So, how do we use these critical values? From your calculations and from the critical value table, you will find if the value of the test statistic you've calculated is greater than the value in the table. That's known as the critical value. Basically, if when you've done your sum, the number you get at the end of the sum beats the value in the critical value table that you have in your jotter, then you can accept your alternative hypothesis. If it does not beat the value, then you must accept the null hypothesis. And that's how we prove an alternative or a null hypothesis. Okay, that's it. That's how to make a hypothesis, and that's our first little steps into inferential statistics. The next lessons will go step by step through how to do each of the major statistical tests.